I'm Ava.
And I'm Beth.
This is Calculus AB.
Are you ready to graph this function? I am. Sally bought a new farm in Milktown. She wants to build a rectangular fence around the barn with an area of 32 meters squared. What dimensions will minimize the perimeter of the rectangle? So first thing I did was draw a picture of this rectangle. X for the width, Y for the length. And then I know that the area is base times height, which X times Y equals 32. I solved for Y, so Y equals 32 over X. Now I know the perimeter is 2X plus 2Y because we have two widths and two lengths. So I made this into a function and substituted the Y. Then I took the derivative of this because the key to optimization is taking the derivative of the equation you want to minimize or maximize. In this case, we want to minimize the perimeter. We multiply the two first, and then I use the quotient rule to solve this. But I recommend you do this part on your calculator because this would be a calculator okay question. After finding the derivative either by hand or on your calculator, you set the derivative equal to 0, and then you solve on your calculator for x. Find that x equals plus or minus 4 root 2. However, dimensions cannot be negative, so it's only 4 root 2 meters. Then you have to go make a number line, so I plugged in a value into 2 minus 64 over x squared. Anything in between 0 and 4 root 2. So I plugged in 1/2 and I got a negative value on my calculator. And I plugged in 6, which is a value greater than 4 root 2, and I got a positive value. So I know that it goes from negative to positive. That would be a local minimum. This is also the only critical point, so it is an absolute minimum.
It's story problem time. This is definitely one of the more challenging optimization problems that I've come across, but it is really good to know how to do, and you can do it. Flamingos fly. Flamingos fly? Flamingos fly faster over land than water. They can fly 15 meters per second over land, but only 10 meters per second over water. A flamingo is at the edge of a 1,200 meter wide river and wants to go to its house, which is 2,000 meters away on the opposite side of the river. Okay, so first of all, before we go any further, I'd like to draw this out. So I made a little point with an F that represents where the flamingo is, and then a vertical line that measures 1,200 meters. So that's the width of the river, and then the hypotenuse of this triangle is the 2,000 meters away where the flamingo's house is on the opposite side. So that's our little triangle there. And then moving on, what the problem wants is what path would minimize its flying time. So we are minimizing time, and minimizing goes hand in hand with derivatives. We use derivatives to find the minimum, and we need to find an equation to minimize connected to time. So we are minimizing its flying time. Do we know a time equation? Not exactly. We know a distance equation, d equals rate times time. So we can take that and adapt that equation and make it so that we're solving for t. So just divide by rate, and then time equals distance divided by rate. And then the next thing I did is I drew a line from F to sort of the middle of the other leg of the triangle, because we know that there's going to be some distance over water and some distance over land. We don't know the specifics yet, but we know that much. Then we want to know what the length of that whole leg is, so you can use sort of reverse Pythagorean theorem and solve for that leg by doing, x squared plus 1200 squared equals 2000 squared. Solve for x, and you'll get 1600 meters is that whole length. And then I split it up, that part that's divided by the little line I drew, I split it up into x and 1600 minus x. And then that line is the hypotenuse of a smaller triangle made up of the x and the 1200 meters. So we know the length of that line, once again using Pythagorean theorem, is the square root of x squared plus 1200 squared. Okay, so we have two different rates and two different distances. Therefore, we need to split the equation into two things and add them together. We have the distance 1, the smaller hypotenuse, and that's over the rate of 10 because that's how fast the flamingo flies over water. And then we add it to the other distance, 1600 minus x, over the rate of 15 because that's for overland. And as you do minimizing, it always brings to mind derivatives because the derivative is what's going to find you the minimum. So we have to take the derivative of this equation, and it's pretty complicated, so you can use a calculator here. And as you see, I brought in my CAS calculator and I got a derivative of x over 10 times the square root of x squared plus 1200 minus 1 over 15. And then to find the minimum, we need to find a critical point. So we need to set it equal to 0. Once again, use your calculator for this. And you get 8 root 15 as the x value when this equation equals 0. And then you have to make a number line to check. You always got to make sure that it's a minimum. And I did check and it works. Plugging in numbers before 8 root 15 will give you negative, and plugging them into the derivative after will give you positive. So we get that 8 root 15 is a minimum, definitely, but we're not done yet. We have to plug it in for x to actually get the distances, because the question is asking what path would minimize the flying time. So we have to actually find the distances. So we plug in 8 root 15 into these two distances. Once again, the square root x squared plus 1200 squared and the 1600 minus x. And finally, we get that in order to minimize flying time, the flamingo should go 1,199.95 meters by water and 1,569.02 meters by land. And that's the end of the problem. That's your answer. It's a very long problem. There's lots of room for error in it, but it's just important to get thinking in this way and understanding what equation you need to take the derivative of, understanding all the little parts of the problem and how they relate to one another, and being able to get that final answer in the form that they are asking for in the question. So I hope that made sense, and keep on optimizing. Be optimistic.